In this video, we'll be learning the logic gates by examining their structure, and we'll be using these gates integrated circuits to experiment how they operate. We'll be making examples using the digital I/O pins of the microcontrollers to better understand how logic gates work. Let's start with the NOT gate, which is also known as the inverter. Here we see the NOT gate symbol, a triangle with a bubble at the output. Here, X is our input and F is our output. The truth table shows that the input is inverted at the output, so if the input is 0, the output will be 1, and if the input is 1, the output will be 0. The CMOS circuit shows the details of the NOT gate. Here we have one PMOS and one NMOS field effect transistors, whose gates are connected to the input, and the drains of the transistors are also connected together to the output. The source of the PMOS is connected to the VCC, and the source of the NMOS is connected to the ground. Now let's see how this circuit forms a NOT gate by checking the behavior of the PMOS and NMOS as a switch. In the small table, you can see that while the gate source voltage is equal to VCC, the PMOS will behave as an open switch and the NMOS will behave as a closed switch. And in an opposite way, while the gate source voltage is equal to 0, the PMOS will behave as a closed switch and the NMOS will behave as an open switch. By this information, we will be able to explain the behavior of the logic gates. In this NOT gate example, as we have 1 in the input, the PMOS will be an open switch and the NMOS will be a closed switch, and the output will be directly connected to the ground, meaning that it will be 0. And if we have a 0 in the input, the NMOS will be an open switch and the PMOS will be a closed switch. The output will be directly connected to the VCC, meaning that it will be 1. Here we can see an 7404 IC containing 6 NOT gates. This is called a hex inverter since it includes 6 or hex inverters. Let's quickly check its datasheet. This is the datasheet of our hex inverter. You can see that it has a wide operating voltage range which is between 2 volts and 6 volts. Let's scroll down towards the pinout. This is the pinout of our IC. You can see that it has 14 pins, 1 for VCC and 1 for the ground, and it has 6 inverters inside. Let's use this pinout in our presentation. Here we can see the mapping of the pins on the integrated circuit. Make sure the pin indicator is aligned. Now let's connect this NOT gate integrated circuit to microcontroller. In this slide you can see the connections to the MSP430. First, we'll connect the VCC to the 3.3 volt pin of the launchpad and the ground to the ground pin on the launchpad. Unfortunately, the first 2 NOT gates of the IC that I'm using are not working, so I checked it and they are always giving high output regardless of the input, so I won't be using them. I'll be connecting the 4 pins of the P1 port as seen in the diagram. At the same time, I'll be connecting 4 red LEDs in order to observe their status. And I'll be connecting 4 green LEDs to the outputs to observe their status. Now let's open Code Composer Studio and create examples to better understand this logic gate. Okay, now we have made our connections from our MSP430 microcontroller to our breadboard, and these 4 red LEDs are corresponding to P1.0, P1.1, P1.2 and P1.3. And the green LEDs are corresponding to their inverted outputs. You see that we have all zeros in the input and they are inverted to 1 at the output. In this first code, we are going to define our P1 port direction as FF, so all the pins will be output ports. And in a while one loop, we are going to first set it to 0, and then we are going to shift 1 bit towards left. First this LED will be on, then this one, then P1.3, so it will repeat itself. And in between we are going to have 1 second of delay. So let's debug this code. And let's click on resume in order to run it on the microcontroller. So you can see that this output is being shifted from P1.0 to P1.3. And at the inverter's output, we see the opposite of our inputs. You can see that whenever we have a 1 in the input, we have a 0 at the output. Let's try another example. In this example, we are going to generate a random number between 0 and 15, and we are going to assign it to P1 out port. This means that we are going to be having 4 of the LEDs being on or off according to our random number. So if we have, for example, 3 as a random number, we are going to have P1.0 and P1.1 on at that time. Let's debug and run this code. Let's click on resume. Now you can see that in the input, meaning from P1.0 to P1.3, we are seeing random numbers. And the inverted output can be observed on the green LEDs. So whatever we have here is being inverted in the output of our hex inverter. In this slide, you can see the connections to the Arduino Uno. First, we are going to connect the VCC to the 3.3 volt pin of the Arduino Uno and the ground to the ground pin of the Arduino. As I mentioned previously, the first two NAND gates are not working, so I won't be using them. I'll be connecting D2, D3, D4 and D5 pins to the inputs, and at the same time I'll be connecting 4 red LEDs in order to observe their status. And I'll be connecting 4 green LEDs to the outputs to observe their status. Now let's open Arduino IDE and create examples. Okay, we made the same connections that we did for the MSP430. You can see that we have 4 digital outputs from Arduino Uno. These are D2, D3, D4 and D5, and we can observe them in the red LEDs as D2, D3, D4 and D5. And the green LEDs are the outputs from the inverter that you can see here. Now let's check our code first. We are defining the D2, D3, D4 and D5, and we are setting all as outputs. And we are sending high voltage to D2 and then to D3, D4 and D5, and the rest will be having low voltage. And in between we are having 1 second of delay. So let's send this code to our Arduino Uno. Okay, now you can see that it started running, starting from D2, D3, D4 and D5, and we can see the inverted outputs at the green LEDs. Now let's take a look at our second example. Now in the second example we have our same connections, same digital pins. Now we have this random number and random number underscore bin, which stands for binary. We are going to again define these digital pins as output, and then for each pin we are creating a random number and we are creating this random binary number. So if it's 0, we are going to send low to that particular pin. If it's 1, we are going to send high. So we do the same for all 4 pins, and then we set a delay of 1 second. So let's send this code to our Arduino. Okay, it's already started running. You can see that we are having random numbers in the input. So it's changing in 1 second. And we are seeing the inverted outputs at the green LEDs. Let's continue with the NAND gate. You can see the NAND gate symbol and the truth table here. The reason we started with the NAND gate instead of the AND gate is that NAND gate can implement any Boolean function by itself. Let me try to clarify this statement. For example, if you connect X and Y inputs together and form a single input, then you will have a NOT gate. Check the truth table. We will no longer have the second and the third rows, and the simplified truth table will be like this, which is the truth table of the NOT gate. Similarly, if we add a NOT gate, which we saw that it can be obtained from a NAND gate, to the output of the NAND gate, the truth table will change into this, and we will have an AND gate. And as a third and final example, if we add 2 NOT gates to the inputs of the NAND gate, we come up with this truth table, which is the one for the OR gate. In this figure, you can see the CMOS circuit for the NAND gate. You can see that only in case that X and Y are equal to 1, which makes both NMOSs behave as closed switch, the output will be connected to the ground, meaning that it will be 0. On other three conditions, the output will be 1, because at least one of the PMOSs will behave as a closed switch. This is the 7400 integrated circuit, which is a quad 2-input NAND gate. The reason it's called quad is that it includes 4 NAND gates inside. Now let's see the connections between the quad NAND gate and the MSP430. We will be making the VCC and ground connections first. Then we will be connecting the P1.0, P1.1, P1.2 and P1.3 to the A inputs of the NAND gates and to blue LEDs at the same time. And we will be connecting the P2.0, P2.1, P2.2 and P2.3 to the B inputs of the NAND gates and to yellow LEDs at the same time. Finally, we will be connecting the outputs of these 4 gates to red LEDs. And you will see in the circuit that we will input these outputs to an inverter and we'll observe the inverted output in green LEDs. You can see that we have made our setup on the breadboard. This is our NAND gate IC here and this is our inverter IC here. So we can observe the inputs in the yellow and the blue LEDs for the 4 NAND gate inputs, and we can observe the outputs at these red LEDs. So these are corresponding to 0, 0, corresponding to the output of 1. Actually, this is kind of a truth table. You can see it very easily. And we have 0, 1, which is corresponding to 1 again, and 1, 0, which is corresponding to 1, and 1, 1, which is corresponding to 0 output. And you can see that on the inverted side, we can see 0, 0, 0, and 1. Actually, this output is the output of an AND gate, because for 0, 0, it's 0, 0, 1, it's 0, 1, 0, 0, and 1, 1, the output is 1. If we check our code, you can observe that the last 4 digits are corresponding to our inputs. And in the P1 out, you can see that we have 0, 0, 1, 1. Actually, these are the blue LEDs, 0, 0, 1, 1. And in P2 out, we have 0, 1, 0, 1 is for the yellow LEDs, 0, 1 and 0, 1. You can play with the code to observe different outputs from the gates. Now let's check the AND gate. This is the symbol and this is the truth table. We only have 1 at the output in case both inputs are 1. And we can obtain an AND gate by adding a NOT gate to the output. This is the sample integrated circuit 7408 that we are going to use in our example. It's called a quad 2-input AND gate. Since AND gate's pins are identical to the NAND gate, we are going to just replace the IC on the breadboard. The connections will be the same as the previous example. Now let's replace our NAND gate IC with our AND gate IC. This is the 7408 AND gate chip. You can see it in focus now. So let's replace the NAND gate with the AND gate. Okay, seems that I replaced it correctly. Let's connect our microcontroller to power. Okay, it works as expected. You can see that we have the same inputs 0, 0, 0, 1, 1, 0, and 1, 1. And this time the outputs can be observed on the red LEDs. You can see that for 0, 0 we have 0, For 0, 1, we have 0. For 1, 0, we have 0 again. And only for 1, 1, we have the output as 1. And you can see the inverted outputs on the green LEDs. Actually, these ones are now the NAND gate outputs. We can change our code to observe the status. Let's replace this alignment. For example, let's say 1, 1, 0, 0 instead. And let's say 1, 0, 1, 0 to have an inverse display. Okay, we have all the 4 conditions for the truth table. Let's save this one. Let's debug it. Okay, and let's click on resume to see the output. Okay, now you can see that the first inputs are 1, 1, which are actually 1 and 1. Okay. The second one is 1, 0. The third one is 0, 1. And the last one is 0, 0. So, and we have the AND gate outputs respectively, and also the NAND gate outputs. This is the OR gate, and this is its truth table. The output is 0 only if both inputs are 0. All other 3 conditions give 1 as output. This is the CMOS circuit. You see a NOR gate whose output is given as an input to the NOT gate. We will not give an example of the NOR gate, however, its operation is also simple. Only if both inputs are 0, the output will be 1, since the PMOSs will be closed circuit to the VCC. And the OR gate is its inverted state. This is the sample integrated circuit that we are going to use in our example, 7432 quad 2-input OR gate. The connections will again be the same since the pinout is identical to the previous integrated circuit. Since the 7432 IC, which is the OR IC, has the same pinout with the NAND and the AND gates, we can directly replace it as well. So let's disconnect the AND gate and connect the OR gate. This was our AND gate. And this is the OR gate. Okay, it seems to fit in place, so let's connect our microcontroller. Okay, what do we have here now? So this input is 1, 1, the output is 1 as expected. 1, 0, the output is 1. 0, 1, the output is 1. And only for both zeros, we have an output of 0. And you can see the inverse of this, which is the NOR output. Let's change the sequence once again. For example, this time let's change it as 0, 1, 0, 1. And let's have all the 4 possible situations. Let's have 0, 1, 1, 0. And that covers the 4 possibilities. Let's save it and debug it. And let's click on resume. Okay, we can see that now we have 0, 0 here, actually, which corresponds to this state, 0 and 0. Then we have 1 and 1. The output is 1. 0, 1, the output is 1. 1, 0, the output is also 1. And we have the inverted outputs on the green LEDs. This is the XOR gate, and this is its truth table. You can see that if the inputs are different, the output is 1, and if the inputs are identical, the output is 0. The CMOS circuit is much more complex than the previous gates. Here you can see that all 4 states are obtained by 4 paths. So let's see these examples. For example, if we have 0 as X or input 1, and if we have 1 as Y or input 2, you'll see that this path is going to be closed. So we are going to get VCC at the output. And for example, if we have 1 as X or input 1, and we have 0 as Y or input 2, we'll see that this path will be closed. So we are going to get VCC in the output. And you are going to see that for 0, 0 and 1, 1 inputs, one of these 2 paths will be closed circuit. So for example, for this one, if we have 1 and 1 in both inputs, we are going to have 0 or ground in the output. And if we have 0 in both inputs, so their inverses will be 1 and 1. So this path is going to be closed, and we are going to get ground or 0 at the output. This is the sample integrated circuit that we are going to use in our breadboard. It's 7486 quad 2-input XOR gate. Since the pinout of this IC is also the same, we are going to just replace it on the breadboard. In this last example, we are going to use the XOR integrated circuit, which is 7486. Since the pinout is the same as the others, we can directly replace it. The last one that we used was the OR gate, and we are going to replace it with this XOR gate. Okay, we inserted it on the breadboard. Let's connect the microcontroller. All right, let's observe the situation. We know that for XOR, when the inputs are reverse, I mean the opposite of each other, then we have one output. Let's observe it. In the first XOR gate, we have 0, 0, so the output is 0 as expected. In the second one, the inputs are 1 and 1, so they are the same, and the output is 0 as expected. On the third one, it's 0, 1, so they are the opposite of each other, so the output is 1. And on the last one, we have 1, 0, again opposite of each other. We have 1 in the output. And at the output of the inverter, we have the output for XNOR gate. For example, if we change the output as being the reverse of each other all the time, so we have 1, 0, 1, 0, we should expect all ones in the output. Let's check it, let's save it, debug, and then resume it. Okay, let's check that one. Okay, you can see that all the inputs are the opposite of each other, 0, 1, 1, 0, 0, 1, 1, 0, and all of the outputs are 1, and the output of the XNOR gate is all zeros. This was the end of the video. I hope it's been useful for you. If you have any questions or comments, please write them in the comment section. Thank you for watching, and see you in another video.